human worker, made of flesh and bone, requires breaks, health insurance, and sleep to maintain a safe cadence on a factory line. A synthetic humanoid, by contrast, is a rigid assembly of motors and metal designed to execute that same task without variation. The financial contrast is stark. A human worker costs $46.30 per hour. The humanoid robot costs 51 cents per hour. Annually, the human position costs over $95,000, including benefits and taxes. The robot's cost is a fraction of that, despite working 3 times the hours. This represents a total collapse of traditional labor economics. For a factory owner, the cost of human physical labor is becoming impossible to justify against a synthetic alternative. This transition isn't just about corporate margins. It is a response to a tightening macroeconomic squeeze. The global supply of working-age humans is shrinking. These UN forecasts show a massive decline in working-age populations across China, Japan, and the European Union by 2050. Traditional automation, machines bolted to a floor, cannot fix this because they cannot move through environments designed for people. With fewer humans available to perform physical work, synthetic labor is becoming a prerequisite for maintaining the global supply chain. Tesla is moving to fill that labor gap immediately. The company is currently retooling production lines in Fremont to begin mass-producing the Optimus Gen 3 robot in the summer of 2026. The plan involves a machine with a $20,000 target price, designed to operate for up to 8,760 hours a year. Replacing a single manual labor position with this hardware saves a company roughly $535,000 over 5 years. In an industry defined by tight margins, ignoring a 90% reduction in productive hourly costs creates a competitive disadvantage that few firms can survive. Legacy humanoids were too rigid to scale. Because they were sensor-poor metal frames, they had to make millions of power-hungry corrections every second just to keep their own weight from toppling them over. The Gen 3 hardware overcomes this with a new extremity, hands featuring 22 degrees of freedom, double the dexterity of previous prototypes. To achieve this, the design mirrors human anatomy. 50 actuators are housed in the forearm, acting as tendons that pull and flex the fingers with enough precision to handle fragile objects without crushing them. This is mechanical intelligence. It's the practice of designing a machine's physical structure to adapt to the environment passively, rather than relying on the brain to calculate every minor adjustment. The hardware is no longer the bottleneck. The robot is finally capable of executing the nuance of human touch. Even a perfect physical body is useless if an engineer has to manually code every individual movement of the arm. Tesla's AI-5 chip solves this by leveraging millions of miles of existing driving data. The same neural networks that allow a car to understand a busy intersection are being used to teach a robot spatial reasoning. This enables zero-shot learning. It's an AI capability where the robot can master a new task simply by observing a human demonstration once, rather than following a rigid script. This allows robots to enter a warehouse like human apprentices, learning and adapting to chaotic environments on the fly. However, a hidden constraint remains. Current prototypes often see their batteries die after only 2 to 4 hours of dynamic work. The industry is looking to solid-state batteries to solve this stamina gap. This chart compares the energy density of solid-state technology against current liquid lithium. Solid-state packs allow for significantly longer runtimes and higher stability, which is essential for a machine that never goes home. Resolving this battery limitation allows the humanoid to move from a prototype phase into a cycle of unrelenting 24-hour continuous labor. These machines won't start in your kitchen. They are heading straight for the industrial floor. The deployment strategy focuses on the 3K jobs, tasks that are kiken, kitanai, and kitsui. In English, dangerous, dirty, and tough. Use cases are already being identified in toxic waste plants, in disaster zones, and battery cell sorting. Jobs that are increasingly difficult to staff with human workers. By taking over the brutal roles humans are already abandoning, corporations can integrate a robotic workforce while minimizing public resistance. For the human worker, this means the nature of a job is shifting away from physical execution. Sociologists call this shadow work. It's the transition toward a managerial role, where human labor is redistributed into the supervision and maintenance of AI systems. Your daily tasks may soon involve managing the charging cycles, software updates, and task assignments for a fleet of synthetic workers. The economic pressure to shift is accelerating. By 2028, the rising cost of human labor and falling price of robotics will permanently cross. A robot that pays for itself in 3 months becomes an economic inevitability. As the physical demands of labor are automated, human value will increasingly be defined by the ability to orchestrate and maintain the systems performing that work.